All right, so I want to talk a little bit about our inverse trig functions, and I'm going to use Desmos to do it. That way you don't have to look at my terrible pictures. So you should be seeing Desmos now, and the first trig function or inverse trig function that we're going to talk about is sine. Now, if you watch the videos talking about inverses, one thing that you may have noticed is that if a function is going to have an inverse, right, it has to be 1-to-1, meaning it has to pass the horizontal line test. But this sine function certainly doesn't look like it passes the horizontal line test. For example, if I draw a horizontal line at y equals 0.5 or y equals a half, well, this horizontal line is passing through our function at lots of different places. So this seems to be a problem, right? Because if sine doesn't pass the horizontal line test, well, how in the world can it have an inverse function? How can it have an inverse at all? And so here's the way that we get around this. We restrict the domain, or we limit the domain of sine to only a portion of the function so that it has that 1-to-1 property, or it passes the horizontal line test. Okay, so there's lots of different ways that we could limit our sine function, but in particular, we're going to choose to limit our sine function so that it only goes between negative pi over 2 and pi over 2. Oops, I can type. So we're going to limit our function to just live between these blue horizontal lines. And I can actually do that here in Desmos. So I'm going to limit our sine function to between negative pi over 2 and pi over 2. Okay. So if you're interested in what that looks like, I'll just pull this over. So this says y is going to equal, I'm limiting my domain to the x values between negative pi over 2 and pi over 2 for the sine function. So notice that that gives us just this piece of the sine function there, okay? And when we do that, well, we certainly now have something that passes the horizontal line test, or is 1-to-1. So by limiting the domain of our sine function to negative pi over 2 to pi over 2, we get something that we absolutely can do an inverse of. Now, one way to think about an inverse is remember that an inverse is a reflection across the line y equals x, okay? So if we could imagine what happens when we reflect our red line across the line y equals x, we would get our inverse sine function. And I'm going to go ahead and graph it. Now there's two ways to graph inverse sine. You could either write it as arc sine, which is another way of saying inverse, or you can use the sine, the -1, which means inverse, okay? Notice that those two functions are exactly the same thing, okay? So it doesn't really matter which one you use. And then if we look at this, okay, notice that the red line is a reflection across the green line of the purple line. Phew. In other words, the sine function with the limited domain and the arc sine function are inverses. Okay? So I'm going to go ahead and get rid of all of our functions except for the arc sine function there. Okay? And let's look at what we notice about the arc sine function. Well, we can think about the domain and range of our arc sine function. Our domain, if I can zoom in a little bit here without cutting off our function. Okay, so it might be easier to actually use this guy to start with. Notice that the domain, so now we're back to our sine function with the limited domain from negative pi over 2 to pi over 2. So clearly the domain of this is pi over 2 to pi over 2. Now remember, inverse functions, right, have this property. How did we get an inverse function? We reflected across the line y equals x, meaning y becomes x and x becomes y. Another way of thinking about that is the domain becomes the range and the range becomes the domain. So if the domain of our original function, the sine function, or the sine function with the limited domain, was negative pi over 2 to pi over 2, that should become the range of our inverse sine function, okay? It's a little hard to see with the labeling that we have, so let's just check that out. Y equals negative pi over 2, that's the bottom of our function, and y equals pi over 2, that's the top of our function. So the domain of the inverse sine function is negative pi over 2 to pi over 2. Okay. Now let's think about the domain of our inverse sine, or our arc sine function. And again, if we go back to our sine function with the limited domain, okay, what is the range of this piece of our sine function? Well, it's the same as the range of our sine function, -1 to 1. If the range of our sine function is -1 to 1, that will become the domain of our inverse sine function. So that says that the domain should go from -1 to 1. Again, with our labeling, that's a little bit hard to see, but let's take a look. Oh, yep, there's the left side of our domain, starts at x equals -1, and the right side of our domain sure goes to x equals 1. Okay. So our arc sine function, which is the inverse of the sine, has a domain of -1 to 1 and a range of -π/2 to π/2. And we got that just by looking at our domain and range of the original function. Okay. All right. So next, we're going to think about our inverse cosine function. All right. So let's do the same thing for our cosine function. Now again, notice that our cosine function, right, has the same problem as our sine function, right? So our sine function also, or excuse me, our sine function was not 1 to 1. Our cosine function is also not 1 to 1. So that means that we're going to think about limiting the domain. Now for our sine function, we limited the domain to go between -π/2 to π/2. But notice that if we do that for our cosine function, we'll have this kind of mountain here, which makes that section of our cosine function not 1 to 1. Okay? So instead, we're going to limit the domain of our cosine function to be between x equals 0 and x equals pi. Okay? So notice that that will give us something that's 1 to 1, so it passes the horizontal line test. So again, I'm going to write that. We'll have y equals, I'm going to limit our domain, 0 is less than x is less than pi for our cosine function. Okay? So that's the kind of chunk of our cosine function that we're going to be working with as we're finding our inverse. Okay? So that means our inverse, again, remember, is going to be a reflection across the line y equals x. So let's see if we can figure out what that would look like. And by us figure it out, I mean Desmos figure it out. So we're going to graph the arc cosine function. Okay? Again, that's the same thing as doing the cosine to the -1 function. Those two are the same function there. And you can see, right, if I folded this page in half across the blue line, the two halves of our function, the purple and the red, would match up. So those are reflections across the line y equals x. Okay? Now let's see if we can't think about the domain and range of our arc cosine or our inverse cosine function. Well, again, it might be a little helpful to go back and think about our limited domain cosine function. Well, the domain of this we limited to be between 0 and pi. So that means the range of our inverse cosine is going to be 0 to pi. Similarly, the range of our cosine function was -1 to 1, which means the domain of our inverse cosine function will be -1 to 1. Okay? So domain goes from -1 to 1, so x equals 1, x equals -1, excuse me, to 1. There's our domain, and our range is going to go from 0 to pi. Okay, so now we kind of have an idea of what our inverse cosine function looks like. Next, we're going to look at our inverse tangent. All right, so now let's think about tangent. Well, tangent's going to run into the same problems as our sine and cosine, meaning that the full graph of tangent is going to fail the horizontal line test. So we're going to need to limit the domain for tangent. To limit the domain for tangent, we're going to limit it in the same way that we limited sine. In other words, we're going to go from -π/2 to pi/2. So we're going to have y equals, I'm going to limit my domain from -π/2 to pi/2. Okay. All right, so notice that we're just getting kind of one of these waves of our tangent function. That's now 1 to 1, meaning invertible. So we're going to reflect across the line y equals x to get our inverse tangent or our arc tangent function. Okay, so there it is. All right, so let's now think about the domain and range of our inverse tangent or our arc tangent function. Well, again, to help with that, it helps us to think about our original limited domain tangent function. Well, clearly the domain of our tangent function is -π/2 to pi/2. That means the range of our inverse tangent function should be -π/2 to pi/2. So let's check that. Y equals pi/2 and y equals -π/2. So notice that this, our arctangent function, the red graph, is sandwiched between those two lines. Those act as horizontal asymptotes for that graph. And then how about the range of arctangent? Excuse me, we just did the range of arctangent. How about the domain of arctangent? That's going to be dependent on the range of our original tangent function. Well, the tangent function has a range of negative infinity to infinity. So that tells me that the domain of our inverse tangent function is negative infinity to infinity, and that sure matches the graph that we see. This is going to go on forever in both directions, so our domain will be everything. Okay, so before we go on to thinking about the inverses for cosecant, secant, and cotangent, I want to work a little bit with what we already have. Okay, so up on the board, I've just kind of summarized what we've talked about. We have our functions, sine, cosine, and tangent. I've reminded us how we've limited the domain in each case. And then we have our inverse functions. Notice that the domain and range of our original function flip-flop, become the range and domain of our inverse function. Okay? Now, we're going to work a couple of examples using this idea. Okay? So I want us to think about trying to solve a question that might look like this. Theta equals arc sine of 1/2. Now the question is, what is this really saying? Okay? Well, we could write this in a different way. I could sort of rearrange this statement to say arc sine, the inverse of arc sine is sine. So in other words, if I took the sine of both sides of this, I would get that sine of theta is equal to sine and arc sine would cancel each other out, 1/2. So this equation, theta equals arc sine of 1/2, is really asking us sine of theta equals 1/2 for what theta? Or another way to sort of reframe this question is to say, when is sine of theta equal to 1/2? Or for what theta, for what angle, is sine 1/2? Okay. Now, we're going to want to use a unit circle to answer this. Okay, so the question is, when is sine of theta equal to 1/2? So I'm going to go ahead and share my screen real quick, which has a unit circle up on it. So let me share my screen. Okay. So here's our unit circle. And remember the question that we were asking is when is sine equal to 1/2? So on our unit circle, remember, goes cosine, sine. So sine is our y values, okay? And we're asking when is sine equal to 1/2? Well, in truth, there's actually a couple different places. Here, sine is 1/2, and here, sine is 1/2. So how can that question have more than one answer? Well, it can and it can't. So that's not confusing at all, right? So I'm going to pull out the answers that we just found from our unit circle. So there were two places that we saw that sine was equal to 1/2. One was at pi over 6 or 30 degrees. The other was over here at 5 pi over 6 or 150 degrees. Okay, so I'm going to stop sharing and we're going to go back to the board. So we saw from our unit circle that there were two places that this was true, right? We saw that when theta was pi over 6 and when theta was 5 pi over 6, that this was true. Okay? If you prefer to work in degrees, we're going to kind of be flexible and try to do both. You can think of this as 30 degrees and 150 degrees. Okay? Now, really, the way this question is phrased, there's only one answer. And to think about why that is, we have to go back to how we defined our arcsine function. Our arcsine function, right? This is saying arcsine equals theta. So theta is in the range of our arcsine function. But the range of our arcsine function is from negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees. Only one of these angles falls inside of that negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees, and that's the first one, pi over 6, or 30 degrees. So technically, 5 pi over 6, or 150, does not answer this question because of the way arcsine is defined. So the answer to theta equals arcsine of 1/2 would be theta equals pi over 6, or theta equals 30. Let's do another example similar to that one. Okay, so here's another equation that's going to involve an inverse trig function. So we have y equals cosine inverse of 0, and we want to solve for y. So this question is really asking us, right? So the analogous kind of equation says cosine of y equals 0. These two things say the same thing. So this is really asking us for what angle is cosine equal to 0. Again, the easiest way to answer this is by looking at a unit circle. So let's look at our unit circle. Okay. So cosine is our x value. So cosine is 0 at 2 places on our unit circle. Pi over 2 or 90 degrees and 3 pi over 2 or 270 degrees. Okay. So again, we're going to have to pick which one of those is correct based on our limitations for our cosine, our arc cosine function. Okay. So again, we saw two possibilities here. We saw that y could either be pi over 2 degrees, which is 90 degrees, or it could be 3 pi over 2 degrees, which is 3 pi over 2 radians, which is 270 degrees. Okay. Now only one of these is correct the way this question is posed. Okay. And again, it's going to have to do with the range of our arc cosine function, right? So this cosine negative 1 of 0 equals y is in the range of our cosine function. But our cosine function's range is 0 to pi. Which value, pi over 2 or 3 pi over 2, is between 0 and pi? Well, only pi over 2, or 90 degrees, is between 0 and pi. So our only answer to this is going to be pi over 2. Okay. Let's look at one more example. All right. Let's look at this example. Find the exact value of tangent of arcsine of square root of 2 over 2. All right, so don't worry, we're just going to work our way from the inside out. So remember, when we're dealing with parentheses, we start from the inside and work our way out. So let's start by figuring out what arcsine of square root of 2 over 2 is. This is really asking us for what angle is sine equal to the square root of 2 over 2. So let's again go to our unit circle. Okay, so remember that our sine is our y values. So where is sine equal to the square root of 2 over 2? Well, here at pi over 4, and also over here at 3 pi over 4. Now remember, our limitations on sine is really we're dealing with our first quadrant here. We want to go from negative pi over 2 to pi over 2. So kind of in this region here. I said first quadrant, I meant the right-hand side. Okay. So we're only going to deal with the square root of 2 over 2 that's over here. In other words, pi over 4. So arcsine of square root of 2 over 2 is going to be pi over 4. So arcsine of square root of 2 over 2 is pi over 4. That leaves us asking tangent of pi over 4 is what? Well, the tangent of pi over 4, notice that this does not have anything to do with inverse tangent, it's just tangent. Tangent of pi over 4 is 1, so our final answer would be 1, okay? Okay, so last, let's go ahead and finish out by looking at inverse cosecant, inverse secant, and inverse cotangent, okay? So let's use good old Desmos to look at these, okay? So here's our cosecant function. Now again, with our cosecant function, it's clearly not one-to-one, so we're going to have to limit our domain in order to get something that is one-to-one, okay? So there's several different ways that we could limit our domain, but we're gonna again use the same limitations that we did for sine, since cosecant and sine are so closely related, and we're gonna look between negative pi over 2 and pi over 2. So I'll have y equals, I'm gonna limit my domain to negative pi over 2 and pi over 2. Oops. Okay, so I'm just looking at this little piece that's inside here, between negative pi over 2 to pi over 2. And then when I invert that, that's gonna be the reflection across the line y equals x, and that's gonna give us our arc cosecant function, also known as the cosecant to the negative 1 or the inverse cosecant function. Okay, all right, so if we're thinking about the domain and range of this guy, okay, Well, that's going to depend on the domain and range of our original function. So our cosecant, we've limited the domain to negative pi over 2 to pi over 2, which means the range of our inverse is going to be negative pi over 2 to pi over 2. Okay. Now, let's think about the range of our original cosecant graph that we've limited to be between negative pi over 2 and pi over 2 for the domain. Well, the range is kind of funny, right? If we look at the range, it looks like there's a big gap here, and that gap is between negative 1 and 1. So the range of our limited domain cosecant function goes from negative infinity to negative 1 and then jumps from 1 to infinity. That means that the domain of our inverse function is going to do the same thing. Notice that the domain here goes from negative infinity to negative 1 and then it stops and it jumps from 1 to infinity. Okay, all right, so next we will look at our secant. All right, so now let's think about our secant graph. Again, as before, we're going to need to limit our domain so that we have something that is actually 1-to-1. So let's think about what that's going to look like. So we have different choices that we can choose, but secant is closely related to cosine, so let's choose the same 0 to pi interval for our domain. So we'll go from 0 is less than x is less than pi, and that's going to give us this little chunk of our secant graph, which is indeed 1-to-1. So we're going to reflect that across the line y equals x, and that will give us our arc secant or our inverse secant graph. Okay, so notice that the purple line is a reflection of the blue line across the line y equals x. Now to think about our domain and range, okay, well the domain of our original graph was 0 to pi. That was the domain of our secant graph when we limited the domain. That's going to then be the range of our inverse secant graph. And how about the range of our original graph, the secant graph where we've limited the domain? Well, the range of that is going to go from negative infinity to negative 1 and then 1 to infinity, which means just like for our cosecant graph, the domain of our inverse secant goes from negative infinity to negative 1 and then 1 to infinity. All right, the last one that we need to look at is we need to look at our cotangent, our inverse cotangent. All right, so last we're going to look at cotangent and think about its inverse function. So once again, we need to limit our domain so that we have something that is 1-to-1. The easiest way to do this is to just take this first kind of section of the cotangent graph, meaning we're going to limit our domain to be between 0 and pi. So let's go ahead and do that. So y equals, we're going to limit our domain. X is going to be between 0 and pi. So we get just one of those kind of, whatever you want to call those, one piece of that graph. So then we're going to reflect across the line y equals x. And when we do that, we'll get our arc cotangent, also known as our inverse tangent, inverse cotangent function. Okay. So notice the blue line and the black line are reflections across that red line y equals x. Okay. All right, so now let's think about the domain and range. Well, we limited the domain of our cotangent function to be 0 to pi. That means the range of our inverse cotangent is going to be 0 to pi, and we can see that here. It goes from 0 up to pi. Okay, and then how about our range? Well, if we think about the range, right, of our original cotangent function, its range is everything, negative infinity to infinity, which means the domain of our inverse cotangent function is going to be negative infinity to infinity. All right, so we've now looked at all 6 of our inverse functions. Remember, the big idea with our inverse trig functions is that we have to limit the domain of our original trig functions in order to get something that's 1-to-1, that is something that we can actually invert or find the inverse of. So when we do that, we get kind of these weird domains and ranges for our inverse trig functions based on how we limited the domain and what that does to our ranges, especially for our cosecant and our secant function. So I've kind of summarized all of that on the board here. Sorry, my handwriting went a little bit down, slipped a little bit down on the right, but we're now going to use these to solve equations that involve inverse trig functions.